Welcome to part 3 of section 4.3. This is the third and final part of the section 4.3 videos. In this video, we're going to be looking at this block that is highlighted here. Specifically, what's covered is now how to use the normal distribution to approximate a discrete distribution, and a special discrete distribution, which we can do this for, is the binomial distribution. And then note that this is excluded because you do it in WST second year. And then this is the last thing that we'll look at the very end. So consider the binomial distribution. So remember, it takes two parameters, n, the number of trials, and p, the probability of success. Let's look at what happens to this distribution now if we vary n but keep p fixed. So if you increase n to 10, if you increase it to 15, and ultimately 25. Have a look at what happens to the shape of the distribution. So here it's a little bit skewed, and here it starts to look less and less skewed until it actually looks quite normal. Now we're going to capitalize on the fact that this thing becomes quite normally distributed for certain combinations of n and p. Suppose you have the random variable xb, which follows a binomial distribution with parameters n and p. You could draw this distribution as follows. So each bar represents a possible value for n, and then the height will be the probabilities. Now, as you can see here, we can superimpose a normal curve. The mean would be mu with variance sigma squared. Now, if we know it's binomial NP, what would you approximate the mean and the variance of this normal curve to be? Hopefully you would agree that intuitively at least it makes sense that this normal curve would have the same mean as the original data, which would be NP, and would have the same standard deviation as the original data, which is the square root of NPQ. Q is just P1 minus P. Now, as I said in the previous slide, we can capitalize on the fact that your binomial almost looks normal for specific combinations of n and p. Now, which combinations are those? That is when you can take the product of n and p and it's greater than or equal to 5, and you can take the product of n 1 minus p, or nq, and it's greater than or equal to 5, then this is a sufficient condition for you to be able to use this normal approximation to find probabilities. Okay, so if you have a case where either one of these conditions is violated, then your distribution might not be normal enough. It might actually be skewed. So it's not bell-shaped enough for you to use a normal curve. So make sure these two conditions hold before you apply it in any case. So now let's have a look at how you find the probabilities. But let's actually just take it step by step, take a step back. So you remember those density curves that we spoke so much about back in part 1? They're back. If we have this graph here, which is binomial, so I'm going to use xb just to make it clear every time, xb, and what if I'm interested in the probability that xb is equal to 3? Okay, here it's equal to 0.4. All right, so remember with a density curve, then the area of the entire rectangle is what gives you the relative frequency or probability of the value or the interval that corresponds to that bar. So in this case, I'm saying this is a density curve, so let's focus on this bar. All right, so here the bar in the middle is 3, but then this whole bar represents minus 2.5 to 3.5. Okay, so this point in between all the values is assumed to lie perfectly in half. All right, and then the height, according to the density, if you go across, it gives you 0.4. So the width of the square is 3.5 minus 2.5, which just gives you 1. And then the height of this rectangle is zero point 0.4. So the area is 1 times zero point 0.4. So notice whenever you have a density curve where the width is just 1, then automatically the height gives you your probability or your relative frequency. Okay, so this is one of those cases where it's just 1. So you could have read it off of this axis. Now, let's say you wanted to use a normal distribution. And I'll explain to you just now why you might want to use a normal distribution. Then this would be the superimposed curve. So it's that red one, but we just focus on it. And if we wanted to find the probability that x is equal to 3, then instead of focusing on this square, we would take the area between 2.5 and 3.5 like we did here, and then we go up to the curve. So ultimately, what that means is now this probability that xb is equal to 3 is approximately the probability that xn is between 2.5 and 3.5. So it's those two values. I'm trying to find this shaded region, but with respect to the normal curve, so I'm going to use xn. Now, I use an approximate sign because you can see here that there's that little triangle here that isn't that, oh, there's a white triangle here that is excluded here. It's sort of included up this side, but it's not necessarily exact, so we use an approximate. So this is where the approximation comes in. Okay, so that means I can approximate this probability using my tables now because I have normal tables. And I said to you just now that there are cases where you'd want to use a normal distribution. Um, Such a case would not necessarily be this one where n is 10, but one where n is bigger than 25. Now, the reason for that is your tables, you can go and check. They only go up to n equal to 25. So you're going to need to use a normal approximation if you want values of n bigger than 25, like 100 or 250. But remember that that condition np and nq must be greater than or equal to 5 in order to use this approximation. So consider the case where you wanted xb less than or equal to 3. How would this look on the normal scale? So this is the same superimposed curve. And now, look, I said the whole bar corresponds to 3. So in order to get all of the 3 bar, I can't just take from 3. I need to take from 3.5. So this probability is approximately equal to xn less than or equal to 3.5. Okay, that is 3 plus 0.5. And remember where the 0.5 is coming from? It's just that little bit that's beyond the 3 to get the whole rectangle. This little 0.5 has a special name. This 0.5 is called the continuity correction. So in a test or an exam, in some of the past papers, you will see that they say use the continuity correction. That's actually a reminder to you that you need to add 0.5 or subtract it. Okay? There are actually some cases where you want to subtract 0.5. All right? So that would be, let's say if I'd wanted x greater than or equal to 3. So that means I want 3, 4, 5, all the way up to 10. Then to get all of the 3 bar, then I need to go back to 2.5. So that's the same as subtracting zero point 0.5. So that zero point 0.5 that we're playing around with is what is called the continuity correction. Now, here are a few examples, and what I'd like you to do is just do what I've done here. Give me the approximate normal. All right, so here I said xb is less than or equal to 3 is approximately equal to xn less than or equal to 3.5. So take this one. If I say xb is less than 5, that's approximately xn less than or equal to or less than what? I think try it out and let's see what you get in these different cases. Okay, let's see if you can get 6 out of 6. I really hope you opted to attempt these questions on your own. If you didn't, you can still pause. Otherwise, let's look at the answers. These are the answers that you should have gotten. Let's look at 2 of them to see how you should have gotten them. If you got all 6 of them, well done. All right, so this is how I recommend you do it, especially while you're still getting familiar with this. Draw yourself a little sketch like this. So this represents like a little snippet of the graph. So remember this thing? It's almost like I just took a little snippet. I took 3 bars. That's usually what you're going to need only. So you draw yourself 3 bars, and then I like to just draw the curve just to represent my normal curve, but it's not the most important thing. And then here they say we're focusing on the 5. So on the middle bar, write the number that you have in the question. In this case, it's 5. And then on either side, write the numbers adjacent. So that would be 4 and 6. So you end up with 4, 5, 6. And then now you look at the sign here. X less than 5. In other words, if you shade what is required, then you would only shade in the 4 because it's strictly less than 5. You don't want the 5 included. So in order to get areas to the left of 5, excluding 5, then you need to get only what's in 4, which is 4.5 there. So that's where you get 4.5. Now in this example, they wanted xb between 4 and 9. So remember, this is the discrete case, so it's important what those signs are. So here we have do the same thing. So I did one for the 4 side, and the other one is for the 9 side. So what I've done, I put 4 in the middle and then 3, 5, and then I shaded in what's required. So this is 4, includes 4. So I shade in the 4, I shade in the 5, and everything to the right. And then this one is strictly less than 9. So I don't want the 9, but I want the 8. So now if I wanted all the area between this 4 and 8, all these shaded regions, then this value here corresponds to 3.5, which is that one there. And then this value here corresponds to 8.5. So that's how you'd get this answer. So you'd follow a similar procedure for the rest of the examples. Now, if there's any example here that you're not comfortable with and you would like a bit of assistance with, please get in touch with the tutors or myself and we can look at it with you. But this is a procedure that I generally recommend for this kind of a thing where you just want to convert it. And then one thing is, okay, so notice when we're working with XB, all of the things on the left are discrete. So you really need to be careful with signs. And then the moment you come on this side, I just copy the signs as is. But remember now, if you want to find this probability on a normal distribution, this is now continuous. So the signs actually are no longer as significant. So less than is equal to less than or equal to, greater than is equivalent to greater than or equal to, and so on, hey? So once you're on this side, it's not such a big deal, but be careful. Be careful. Only once you've moved to the x normal side is it not such a big deal. Yeah, let's continue. Okay, so let's do an example now, all right? So now we want to find a probability. So here it says use the normal approximation to estimate the probability that xb is greater than 5. All right, so if you'd like to try it on your own, I think you should try it. So what you'll need to do, just a quick overview, double check that this property is satisfied. If it's satisfied, then you can do the normal approximation. So you'll need to convert this probability into an xn probability. And then from there, you're now going to use your normal tables. You'll standardize with this mean and this standard deviation and use your normal tables as usual. So try this example for yourself, and then we'll see in the next slide what you get. Okay, so the final answer should have been 0,3745. Give yourself a pat on the back if you managed to get that. And this is how you should have done it. So you'll do the same thing. You draw a little sketch for yourself and then identify what is required. So in this case, 5 is not desired. So you need to make sure you exclude all of the 5 bar. So you do that by going up a little bit to 5.5. Okay, so you end up with xn greater than 5.5. And then, as I said earlier, you are going to standardize. So you're going to take this xn, subtract the mean and the standard deviation to standardize. So in this case, the mean is 5. And remember, the mean for the normal is the same as the mean for the binomial. And you know the mean for the binomial is given by NP. So that is 10 times zero point 0.5, which gives you positive 5. And then for the denominator, to get the standard deviation, it's NPQ. So that is simply this answer that you have here. Okay, so that will give you Z greater than 0.32, and you can find 0.32 in your tables. And then that'll give you 1 minus probability of Z minus probability of 1 minus Z less than 0.32, or which is equal to the final answer. Okay, so that is how you would have done this one. Alternatively, this is another way of looking at it, hey? I just want to emphasize to you that this normal approximation thing, you could have done it a little bit later. Like if you didn't want to use the complement rule here, you could have used it here before you converted it, okay? And you'll come to the same answer. So remember, our table only gives us left-hand probabilities. It doesn't give us right side. So you could have gone ahead and used the complement rule here before you found the normal approximation. Now, I cannot overemphasize how important it is that you watch out for your signs if you're going to do it here. So remember, the signs aren't as important because they're the same for the continuous, but for the discrete, you better be careful here. So if you take xb greater than 5, then that means you want 1 minus the probability of xb less than or equal to 5. So here you don't include the 5, and that will be 1 minus the 5 included. So be very careful if you're going to do it here. All right. And then now, what you would do is then do your approximation at this step instead of doing it here. So I've been trying to emphasize just now that here I put greater than and I put less than, like it didn't really matter because it was continuous, but here I had to be careful with the signs. So now here we want the 5 included. So if you draw yourself a sketch and you shade it in, you'd include the 5 bar. So that means you need to go up to 5.5 to include the 5 bar. So it's 1 minus xn less than or equal to 5.5. Now, this value here, you're going to standardize it in the same way here. You'd subtract minus 5 and you divide by the same standard deviation that you had here. So it's almost what you did here, but now it's just only strictly is less than or equal to. Now that will give you 1 minus z less than 0.32, like what you have here. So ultimately you end up with the same final answer. Okay, so whether you use the complement rule here on the binomial side or whether you use it on the normal side, it is fine. You will come to the same answer provided everything is correct. However, it will be easier doing it on the normal side because you don't have to be so careful about the signs the way that you have to be for the discrete binomial case. Here is a further example that you can also attempt on your own. You can pause the video now if you'd like to give it a shot on your own. Okay, if you did do this one on your own, check your answer. Did you get 0.0146? Let's see how you get to this. Okay, so let's follow that same procedure. Identify a random variable. So that's y is the number of patients that the antibiotic is effective for. Okay, and then it's a binomial 25, 0.7. So this really serves as just a highlight why it's so important for you to be comfortable with your chapter 3 work. So you needed to have picked up that this thing has a binomial distribution. So you can see here that you have this fixed probability of success. That is being a success is being effective. And then you have a fixed number of trials, which is your 25 people. And then here they're saying, what is the probability that it is effective in at most 12? So at most. So for me, when I see at most, I think of it as maximum. Just think of it in terms of English because I know many people get confused. If I said that at most 5 people can come to my party, then that means don't you dare bring me more than 5 people. You can bring me maximum 5 inclusive, but don't you dare come with 6, 7, or 8. So just think of it in terms of a real world example, and maybe that'll help you come to it. But whenever I see at most, I replace it with the words maximum. Okay? And whenever it says at least, I replace it with the words minimum, okay? So in this case, you need to identify the probability. We'll look at that just now. But first, let's just get the mean and the standard deviation. So you'd use a formula from your tables. So your NP and 1 minus, and the square root of NPQ. And these are the answers that you should have gotten. Okay, so we said at most 12, or in other words, maximum 12. That is less than or equal to 12, right? And in this case, y is this binomial. So we need to convert it to our normal case using that continuity correction. So remember, you need to just add or subtract zero point 0.5 to get it onto the normal scale. So it should be approximate. So not too big a deal, but I would have put an approximate here had I noticed earlier. And you'd have 12 now. You want the 12 included, so that means you need to go up a little bit to 12.5. All right, so that's where you'd get that. And then remember to standardize, you subtract the mean and divide by the standard deviation. And then that's where this term comes from. And then you'd get minus 2.18, which you can find in the tables, and you should have gotten 0.0146. The exact binomial probability would have been 0.0175. So you can see why we call this an approximation. It is not the exact value. This one you could have found in the tables because it is 25, but if it was anything bigger than that, there's no tables for that you have. So in other words, you could have interpreted this final answer as there is a 1.46%. So that converted as a percentage is 1.46%. You'd say there's a 1.46% probability that the antibiotic is effective in at most 12 patients. Now, in your textbook, they give you a couple examples, and I want to look at those. So these ones are now just a general discrete distribution that's approximately normally distributed. So it's not necessarily binomial, but you still use the same principles. So in example 4.25, it says IQ is known to be approximately normally distributed with those parameters. So highlight approximate. Let X equal the IQ of a randomly chosen person. All right. What is the probability that x is greater than or equal to 1.25? Now you are already in a position where you can work this out, so you can definitely try on your own, but I'm gonna go through it. So the first thing you're going to do is find that approximation. So in this case, you have 125 and you want to include all of the 125 bar. So you need to go back a little bit. So you subtract zero point 0.5 and you get 124.5. All right. And now you're on that normal scale. So all you have to do now is use the normal distribution. So remember, to standardize, you need the mean and the variance. So in this case, this x, we're told that it is approximately normal, all right? We're not told binomial or anything. So if it's approximately normal with these parameters, then we're just going to use those parameters as is. Remember, we just want the mean and the variance to standardize. So we'll take the mean or the approximate mean of the original data and take the approximate standard deviation. So that means you'll have 1245 minus the 100 divided by 15, which is there. And then if you complete this and use your tables, that will give you 0.0516. And just a reminder, just to emphasize it, that zero point 0.5 that we subtracted is your continuity correction. So just remember that term if it does come up, because it will often come up a lot. Okay. So that is how you do that example. So here, in case you hadn't noticed when we started, IQ is not continuous. Remember, no one has an IQ of, 101.59 or anything like that. It's whole numbers, but they say it's approximately normal. So that's why it's a case where we are using that approximation that we were doing previously, okay? So let's have a look at one more example. So it's the same question, but what if x is equal to 125? Okay, this one's a bit new. We haven't seen an equality yet. So you can do it on your own, but let's look at the answer as well. You can pause it if you would like. This one now, you draw that same little graph of yours, and then if you shade in the 125 bar, then that means you want everything between 124.5 and 125.5. So you'll see these two values cover the entire 125 bar. So that is what you do with an equality. So just watch out for that. That's important. And then from here, you're going to standardize, same as before. Subtract the mean and the standard deviation. In this case, you have 1.63 and 1.7. So remember, it's FA minus FB. Okay, so your 1.7, all right, is your MFB. So 1.700 is 9.554, and then your 1.63 is your FA, 9.484, which you also find in the table, and that gives you 0.007. And just another reminder to make sure it sticks, the continuity correction is that little 0.5 that you subtract or add. Okay. Here are a few examples that you can practice. I'm not going to go through the memo here. You can consult for assistance if you don't get these answers, but here are the answers. 9.9664, and those are the other three. All right, so I just want to conclude with a summary now of what we've just been doing. So like I said, chapter 4 is so nice. You just need to understand and remember the techniques. So let's talk about the technique just in a summarized view for you, and then we'll round up. So remember, if you get a question where you need to approximate a discrete distribution with a continuous distribution, in this case, the normal, specifically the normal, right? I recommend step 1, draw a sketch. All right, so if you consider my example here, all right, you draw a cute little sketch, 3 bars, and then you put the number that they have in your inequality in the middle. So in this case, it's a 3, and then you put the numbers that are adjacent to it. Then shade in the region that's required. So here it says less than or equal to 3. So that means it includes 3. So you shade the 3 and the 2. Then you find the approximate normal and use the continuity correction. All right. So this is approximately now on the normal scale, less than or equal to 3 plus 0 0.5. All right. So you want to include the 3, so that's why I went up to 3.5. And then remember the continuity correction is when you add or subtract that 0.5. And we saw different examples. Some we had to go down 0.5, some we had to go up. But that point 0.5 is what we refer to as a continuity correction. So once you've reached this step, then you standardize, okay? And then the mean is just the expected value from the discrete distribution. So in the first case, it was binomial, which was NP. In the second case, they gave you an approximate distribution for your IQ. So you just took the mean from there. And you do the same thing for the variance. Take the variance of the original discrete data and use it to standardize. And then you proceed as usual to find your probabilities. After you've standardized, use your tables, and then voila, that brings you to the very end. So just before we round up, for the moment generating function for the normal distribution, you do not have to um, do the proof. That is covered extensively in WSC 2 and 1, so that's why I'm omitting it here. So you are still going to do it, just not at this stage. And now, if you go in your tables, this is the moment generating function for the standard normal. Okay. Oh, it's actually for the non-standard normal. For the standard normal, you put mu equal to 0 and sigma squared equal to 1, actually, because you have specific values. So this is for a general normal distribution, all right? And then in the study guide, it says you need to be able to use MXT to show that the mean is mu and sigma squared. This I'm leaving to you as self-study. So remember from one of our previous sections, we showed that if you um, find the derivative and substitute 0, that's going to give you the mean, and then you do something similar for the variance. So that's something you should be able to do for this function, okay? So that brings us to the end of part 3. I hope you enjoyed this video. I wish you all the best.